Hello, my name is Winnie, and we are the Computational Chemistry Group, and we are from Stuyvesant High School. Our project is a study of alternative fuels using experimental and computational chemistry. Who are we? What is computational chemistry? What do we do? Well, here's a methamphetamine to understand what we do. This is what people think we do. This is actually what we do. Microsoft Excel sheets. In all seriousness, what is computational chemistry? Computational chemistry involves computer simulations, algorithms, and theoretical principles to understand and find properties of atoms, molecules, and reactions.
Hi, my name is Carmen. So, what did we do? So the aim of our project was to compare and evaluate alternative fuels using computational simulation calculations and also lab experiments. So some of the questions that we asked ourselves are, what are some alternative fuels? How can we computationally calculate the efficiency? And how can we determine the best alternative fuels? And some of the characteristics that we thought were important were environmental influence. Of course, we wanted minor impact on the environment, and we wanted a low cost. Also, it had to be abundant, and it had to be efficient, and that was our focus, which we used our computations to determine by looking at the thermodynamic data. So why do we do this? And the reason is because the demand for alternative fuels continues to grow as our naturally occurring fuels are running out, such as the non-renewable resources, petroleum and natural gas. And the harmful emissions that they give off are ruining the environment, and the climate patterns are changing, so global warming has become an important issue today. Population health has declined, and sea levels are rising due to global warming. Also, ocean acidification has damaged marine life.
Hello, my name is Melanie, and before we can go into our project, we need to define a few key terms, and the first one is combustion. So, what is combustion? Combustion is a chemical process in which a substance is ignited and oxidized, and in turn produces carbon dioxide, water, and heat. So, in other words, it's like burning. And in our case with fuel, air is used to supply the oxygen, and due to the high temperature and presence of nitrogen, NO2 is sometimes created, which is a free radical and a harmful emission to the ozone layer. On the screen are general basic combustion equations on hydrocarbons and those with oxygen, and nitrogen. Oops. And so the next term is heat of combustion. And so heat of combustion is the amount of heat a substance gives off when it's combusted. And so tying it back to our experiment, obviously the amount of energy a fuel gives off is very important. And so we spent a lot of our project trying to predict heats of combustion. And we'll go into the methods we used.
Hi, my name is Daniel, and I'm going to talk about two ways that we calculate these heats of combustions. The first way is a very simple way using bond energies. So the concept behind this is really simple. Energy is used to create break bonds, and energy is released when we make bonds. And so you can see on the formula up there, the sum of the bond energy of the reactants minus the sum of the bond energy of the products equals the amount of energy released. And if the molecules are not in gas phase, you can use the heat of combustion, sublimation and vaporization to change them into gas phase. The other method is using the computer program Spartan. It's a molecular modeling and computation program, and you can see up there we model sucrose. So why are we using Spartan instead of bond energies? Well, even though bond energies is very simple, it also has a lot of limitations, and also it gets really inaccurate as the molecule gets bigger. So as you can see up there, there are three limitations of bond energies, which is molecular geometry like resonance structures and isomers, correlation energies, and vibrational energies. And for the most part, Spartan can actually get rid of these limitations and give us really accurate calculations.
It's the right button.
Okay, so my name is Shadman, and I'm going to add on to what Daniel was talking about. After you guys just learned about Spartan, I'm going to talk about the computational procedure. So we chose a test set of about 31 molecules of varying sizes and bond types and atoms. The main atoms in these molecules were carbon, hydrogen, oxygen, and nitrogen. These molecules range from methane and butane to much larger molecules like aniline, lactic acid, sucrose, urea. The reason for this is we wanted to test a variety of different molecules to get a sense of whether or not the heats of combustion that we predicted through the Spartan program would accurately reflect the literature values that we had at standard state. Yeah. So there's a bunch of different Spartan methods that we used. The two main types of methods, the first one is the semi-empirical methods. There are 4 semi-empirical methods that we used: AM1, RM1, PM3, and PM6. These methods, those are the semi-empirical methods. These methods use Gaussian functions as parameters, as well as chemical approximations, due to things like electron correlation, which they don't really account for. And with this, they can give us, they can try to accurately reflect experimental data, and we get values from there like heat values and energy values. The other type that's more complex is density functional theory. And the type of density functional theory method we used was B3LIB. This is much more complex. Another big part, as you saw before, about the computational chemist is that we use Excel spreadsheet computation. A big part of it is finding the values that we use and then using them to find the heats of combustion. The two main values that we used for every molecule was enthalpy and energy. Enthalpy is essentially the heat content of a system, and energy is just the energy of the molecule. After calculating heats of combustion, we calculated them 2 different ways. The first being a thermodynamic manipulation of E plus PV, which is energy plus the product of pressure times volume. That equals enthalpy, and by thermodynamic manipulation, that equals energy plus the R constant times the temperature. Because the temperature is a variable right here, we have 2 different values. One for standard temperature, like room temperature here, and one at ignition temperature. Ignition temperature is when a compound spontaneously ignites in nature. The reason we wanted to account for this is we wanted to see whether or not maybe the heat is there's a lot more heat released, or maybe there's less heat released at higher temperatures.
Hi, my name is Jessica. So how exactly did we find the best computational method? So as you can see, first we graphed all 11 methods against literature values, and in order to determine the linear regression or the R-squared value. However, we realized that all the R-squared values were too similar to each other, so we didn't view this method of comparison as reliable. So we implemented 4 other statistical factors, such as average percent error, standard deviation of average percent error, average unsigned error, and standard deviation of average unsigned error. Then we ranked all the computational methods from 1 to 11, 1 being the best in each statistical category, and then we tallied up the sum of rankings for each method. So in this case, a lower sum would be preferred to a higher sum, and we found that RM1, method 1, which used the concept E plus RT, had the lowest sum or the highest average rank. It also had a difference of 8 from the second best method, B3LIB, and it further reaffirmed its position as the best method.
This is the button to change, right?
Hi, my name is Rafael, and when you're choosing a fuel, probably the most important characteristic you're looking for is the amount of heat of combustion it releases, the heat it releases after combustion. But there are other factors that you have to take into consideration when you're deciding whether or not a fuel is practical. You have to decide what the heat capacity is. You would want a low heat capacity because the lower the heat capacity is, the less energy you need to reach a compound's ignition temperature versus the temperature where the compound spontaneously ignites. You would want a low cost, obviously. You would need a low toxicity, a low corrosivity, because when you're transporting or importing fuels through barrels or pipes, if it's very corrosive, that's problematic. And you will want a low kinematic viscosity, which is defined as the absolute viscosity divided by the density. Kinematic viscosity becomes a huge factor while you're actually putting the fuel into application inside an engine. If fuel has a high kinematic viscosity, then it has a lot of resistance. If a fuel has a low kinematic viscosity, it travels as the smoothest at a laminar flow, and it's much more efficient. And you would want a high availability. So this is a chart where we found like the top 5 for each of the characteristics. As you can see, the highlighted compound, biodiesel, appears in many of the different characteristics of the top 5, so we decided that it was one of the most efficient fuels for usage. Also notice that not all the characteristics has a number after it, so methane and lowest heat capacity has 34.92 joules per mole Kelvin. But if you're talking about something like sustainability or toxicity or corrosivity, there isn't really a quantifiable way to measure that. So what we did for something like toxicity is that we measured the time it takes for a certain compound to kill someone. So the longer it takes for something to do its most harmful effects, the lower toxic it is. And if it takes a very short amount of time for something to do a lot of damage, then more toxic it is.
Hi, my name is Simon. So we found that biodiesel was a very promising alternate fuel. So we decided to synthesize it from oils in our lab. So we followed a procedure from Loyola University of Chicago Biolabs. And in order to make a biodiesel from labs, it needs to be a transesterification reaction. So oils typically are made of triglycerides, which are a glyceride compound attached via ester bonds to 3 fatty acids. When you add alcohol to it, it breaks up the ester bonds and changes the long hydrocarbon chains into fatty acid methyl esters, which are known as biodiesel. And in order to get the reaction going, we added a base catalyst. So here you can see the oils that we use. We use a variety of oil ranging from extra virgin olive oil, expired extra virgin olive oil. We also used soybean oil, hot dressing oil, and waste vegetable oil from a fryer that we got in Wendy's.
Hi, I'm Michael. So how do we actually make the biodiesel? Well, first, not all of our biodiesels are clean. Some need to be filtered before we can use them. In our case specifically, we used waste vegetable oil from Wendy's that had to be cleaned because it had things like French fry flakes and other dirt that couldn't be used in our reaction. So we filtered it by using a water aspirator vacuum trap, which creates a vacuum that pulls our oil through a filter. And as you can see on the photo on the right, well, we ended up with a thick layer of gunk that came from the oil. And this, by the way, is what you have on your French fries. And so now we could actually convert our oil into the biodiesel. And so we converted it using a process known as transesterification, which is when we take the triglyceride or fat molecules inside of the oil and convert them into fatty acid methyl esters, or FAMEs, which are the main components of biodiesels. And we transesterify the fats by mixing the oil with an alcohol, or in our case methanol, and a base, or potassium hydroxide. Afterwards, we stimulated the reaction by agitating it. And so after the reaction took place, we ended up with a mixture of both the biodiesel that we wanted and leftover reactants and waste byproducts that we wanted to get rid of. So we let the mixture settle so that all the waste would settle to the bottom. Lastly, since not all the waste had been gotten rid of, we also washed our biodiesel by adding water to it, so that as the water fell through the oil, it would drag down all the water-soluble wastes, and all of the things that we didn't want would fall to a layer at the bottom, which we then separated. So here's a photo that shows you 3 of our biodiesel and waste mixtures standing in separatory funnels. And so as you can see, the clear layer at the top is the biodiesel that we want, And on the bottom, you have a dark colored layer of waste, which we then drain from the bottom, and ta-da, you have your biodiesel.
Alright, hello, my name is Mafuzo Islam, and this is a video of a gas chromatography mass spectrometry, or GCMS for short. So what we use this machine for is to find what compounds the biodiesel was composed of. So what this machine does is it separates the compounds in the biodiesel by mass and polarity. So right now what it's do, sorry, we're having some technical difficulties, but what it does is first it washes the syringe with a compound, and then it washes it with 2 times with the biodiesel, and then on the 3rd time it inserts the biodiesel into this long column, this circular column, where as a gas, and it separates it in there through mass and polarity, and the results come out like this. So the top part, the top is where you have the total ion count, or all the peaks. So each peak represents a separate compound. So if you zoom into one of the peaks, you get the area of the peak, and you get a fragmentation pattern for that peak. So what the GCMS software does is it compares that fragmentation pattern that you got from the experiment to a library of fragmentation patterns from NIST, or the National Institute for Standards and Technology. And so what some of the compounds that we got were hexadecanoic acid, 9,12-octadecanoic acid, and these are all methyl esters, which we expected. However, there were some compounds like 2-hexanol and 11-hexadecene-1-ol, which are already there previously from the oils that we used.
All right, so when we wanted to figure out which one was the best biodiesel, we had to measure some specific properties like density, viscosity, and specific heat. So you can see that density is equal to mass over volume. We just weighed the biodiesel, and we found the volume of it to divide and get density. And then to get viscosity, we used the formula. Viscosity is equal to 2 times the difference of the density of the sphere we dropped inside and the biodiesel times the gravitational constant multiplied by the radius squared of the sphere dropped, divided by 9 times the velocity of the ball falling. These two are important because if the biodiesel is too dense or too viscous, then it wouldn't be like an efficient fuel to use for engines. And specific heat is also important because, like we mentioned earlier, we needed it to raise the temperature of the engine quicker so it can auto-ignite. All right, so here we have a chart of biodiesel properties that we just mentioned. There's purity, density, viscosity, and specific heat. And the highlighted ones are the highest ones. Okay, so at the bottom we have the literature values, and you can compare how close each one is to the values that we measured. And most of them were pretty close except for the viscosity, which were off, but they were fairly accurate.
So here we actually have a demo of how we calculated the heat of combustion, and this was one of my favorite experiments because we actually got to burn our biodiesels that we created. So here, play that. That's a little loud, but as you can see, it takes a while for the biodiesel to actually ignite because it has to get to the proper temperature. So we used propane, which was much faster than using a match, which didn't actually work. And so, as you can see, when it started burning, we took the biodiesel in the tin can and we placed it underneath the round bottom flask with the water. So you can just watch as we're doing that. And we recorded the temperature before and after the biodiesel stopped burning. And then we use this equation right here using the mass of the water and the mass of the biodiesel burned, as well as the change in temperature and the specific heat. Do the clicker. So here we actually have a chart of the experimental heat of combustions, the ones that we calculated with Spartan using the best method, which was RM1 method 1, which was RM1 plus ERT, as well as the Spartan calculations at the ignition temperature. And here you can see that we used GHC, which stands for gross heat of combustion, and that accounts for the heat of condensation of water. So our experimental heats of combustions were actually very, very low comparing to the ones that we calculated using Spartan. And we think this is because of an experimental error in the laboratory, because it wasn't really an isothermal system, so heat escaped from the sides of the round bottom flask. But we can see that the expired olive oil had a very high Spartan calculation of heat of combustion at the ignition temperature, which was very surprising because it did have a low purity because it was expired, so it had a lot of peroxides. But at the standard temperature, the extra virgin olive oil that was not expired did have the highest heat of combustion. So now we're going to play a little video. Just because one of our members wasn't able to be here today, so we still wanted him to present, so we'll just show his video. Put the sound on.
I'm here to discuss our final conclusions. Our first conclusion is that RM1 method 1 is the best method for accurately computing heat of combustion values for molecules. This is surprising given that it outperformed the more complex density functional theory model using the V3 functional. This means that we need to investigate more to see if more complexity truly brings more accurate results. This can be done by expanding the set beyond 31 molecules, as well as by using other methods to calculate heat of combustion, such as Hartree-Fock and Menel-Tussle. Our next conclusion was in regards to our experimental procedure. Our experimental procedure found the heats of combustions of our biodiesels to be in the range of 1 to 2 kilojoules per grams. This highly contrasted our calculated values using Spartan, which were in the range of 35 to 38 kilojoules per gram. In addition, to further strengthen the Spartan calculations, we researched the heat of combustion of biodiesel and found it to be in the range of about 40 kilojoules per grams, which is very far off from the 1 to 2 kilojoules per grams that we found in our experiments. This error is likely the result of either impure biodiesels or heat loss to the surroundings. Our last conclusion is in regards to the research that we did. We were able to dismiss many possible alternative fuels such as naphthalene, bioethanol, and bioethane due to characteristics such as toxicity, corrosivity, and renewability. However, there is hope. We did find that both ethane and biodiesel are very strong in many areas. As a result of this, using both computational chemistry as well as experimental data, we should further investigate these fuels to see if they truly can replace petroleum as the main fuel of the future.
All right. So that's Eli, one of our team members. Here. And so we would like to thank, of course, our sponsors, Con Edison, the New York Building Congress, as well as the Albert Merkin School of Engineering here at Cooper Union, and all the instructors that gave us demos that really helped us understand our project better and the knowledge behind it that we needed. And we would love to thank our TAs that were there with us every step of the way, giving us advice, and just really being there all the time. And of course, our professor who really helped us, who guided us through the complicated world of computational chemistry, and we're extremely thankful for that, and he was super supportive. And we would also like to thank Wendy's for being the only fast food chain that would actually give us waste vegetable oil to use. So we were very thankful. Thanks.